section, we're going to talk about the core concepts in Dataflow and terminology so that you can understand everything else that we discuss afterward. Let's go over P collections and elements first. A P collection is a distributed data set. It's essentially the object that you put into your pipeline and what you get out of the pipeline. So in this case, we have three attributes: name, age, and city in our P collection. An element, as defined here, is a single entry of data. In our example, each row represents one element, and each element has three attributes: name, age, and city. So this is a simple table with a collection of data elements, each row being an individual element in the P collection. But even though when we visualize a P collection, it essentially looks like a table, the important difference is that P collections are distributed data sets, and we're about to discuss what that means. P collections are not stored as one big centralized data set, like we usually imagine when we think of tables or databases. Instead, they are spread across multiple nodes or machines. In this visual example, we have a P collection with 5 rows, and the rows get distributed across the worker nodes in the cluster. Each worker node, as you can see on the right, is responsible for handling a subset of the overall data set. In this case, our example P collection, visualized on the left, has been broken into different parts. And the elements within the P collection are divided across these worker nodes, which allows them to process data independently. For example, one machine might be handling the first few rows, while the other handles the next few rows, and so on. This allows for greater scalability, as you can add more worker nodes if you need to handle more data. And it also ensures that processing can happen in parallel, which makes the whole operation much faster. So the important takeaway here is that P collections are inherently distributed by design, and this ensures that large-scale data processing can be done efficiently over many machines. On this slide, we introduce P transform, which is a general concept in both Apache Beam and Dataflow, and it's very important. A transform, to back up a second, is a general term for any processing operation applied to data. We've talked about data transformations or transforming the data. In Dataflow, P transform stands for pipeline transform. And so it's a term for Apache Beam and Dataflow. It means taking data, perhaps messy or unfiltered in some way, processing it, outputting a new data collection, and that output is usually more clean or aggregated in some way. So in the visual, on the left, we have messy data represented by dots in various colors and with no real organization. And after the P transform, the data is organized and clean, as shown on the right side, ready to be used for analysis or further storage. So there are several types of P transforms available for you to use. Each serves a different function for handling and processing data. We'll be covering the main ones in the upcoming slides and focusing on those that are most relevant for the exam. In this slide, we're looking at 2 key concepts used in Dataflow, Pardue and DoFun. Pardue is a type of transformation that gets applied to each element in a P collection. It's particularly useful for filtering or extracting elements from large datasets. For example, if you need to remove invalid data or select only certain elements based on a condition, you would use Pardue to achieve that. DoFun is the custom logic that gets applied to each element as part of the Pardue transformation. It's essentially a function that you write to define how each element should be processed. So whether you're validating, filtering, or modifying data, the DoFun dictates what happens at each element in the data set. So to make this concrete, let's walk through a diagram below. On the left side, we have a P collection of customer records. Each row in this table is a single element representing a different customer. In this case, our task is to filter out the inactive customers. So the Pardue operation is represented by the funnel in the middle of the slide, It's what filters out inactive customers. And as the P collection flows through, the do fun applies a custom logic that checks whether a customer is active or not. The do fun is that custom logic. As a result, inactive customers are removed, and the P collection that exits the funnel on the right side now only contains active customers. This process illustrates how Pardue and DoFun can be used to refine data sets and apply transformation logic at the element level. On this slide, we're going to cover side input and side output. So let's look at side input. Side inputs are supplemental data provided to a transformation, often useful when we need to refer to external references during processing. So for example, we might have lookup tables or configuration data that our transform can reference while processing each element of a P collection. The additional data helps enhance or inform the main processing logic that's applied to the elements. And then we have side output, which refers to additional output P collections that are created when we direct some results to alternate destinations or different outputs. This is useful when we want to handle some elements differently from the main output, like sending error records to a separate location for later investigation. You could use it to filter out errors or direct specific data down a different path in your pipeline, ensuring that the rest of the data continues processing in the main flow, while special cases, such as errors, again, are handled elsewhere. In Dataflow, side inputs and outputs provide some flexibility in how we process and organize our pipelines. Now we're going to talk about group by key, which is another type of P transform. Let's start by looking at this example. We have on the left a P collection of key value pairs. We see keys like apple and banana, each associated with a number, probably something like the count of each of those fruits. And so what happens when we apply group by key? The result on the right shows that essentially we group all values for each key together. So all the values associated with apple are combined into a single iterable, essentially a list. The same happens for banana, which now groups 4 and 6 together. So if you've used SQL before, this is similar to the group by clause in SQL. However, in SQL, when we use group by, we group rows by a column, and we usually apply an aggregate function like sum or count. But in group by key, we group values by a key, but instead of directly applying an aggregate, we get an iterable list of values that then we can further process and aggregate if we want, for example. So this method allows for further processing and transformation on the grouped data. It offers more flexibility compared to the direct aggregation that we typically see in SQL, but it's also kind of giving us, an initial upfront step of creating a list or an iterable first before doing any aggregations. Now let's look at co-group by key. On the left, we have 2 P collections. The first contains fruits and their counts, and the second contains fruits and their characteristics. Both P collections share the same key, which is the fruit name. When we apply co-group by key, let's look at what we get. It combines the 2 P collections by their common key. So the result is a new P collection where each key or fruit is associated with lists or iterables of values from both input P collections. So co-group by key allows us to combine multiple P collections by a common key, and we get an output P collection. As input, we provide 2 or more P collections with the same key, but different value types. The result is a single P collection with a key and lists of values from each of the inputs. So this is especially useful for merging data sets that share the same keys, like counts and characteristics of items. So combining the data, we can then perform further processing on the grouped data, just like with group by key, but across multiple data sets. So in this case, we had, a P collection with fruits and their counts, and a P collection with fruits and their characteristics. So the keys matched each other, but the actual values associated with the keys were different. One was numerical, one was describing its counts, and the other was describing its characteristics. Co-group by key allows us to combine them into one output P collection with iterables from each of the input P collections. Now let's look at flatten. We can do this with an example as well. On the left, we have 3 different P collections. Each contains different fruits and their counts. P collection 1 has apple and banana. P collection 2 has orange and pear. P collection 3 has grape. And then after applying the flatten transform, we end up with a single P collection that combines all of these elements: apple, banana, orange, pear, and grape. Notice how the content from the original P collection stays the same. They're just concatenated into one. So let's break down what flatten does. It merges multiple P collection of the same type into a single P collection. Pretty simple to understand. That's useful when you need to combine data sets that have the same schema or data structure. It does not alter the content of individual P collections. It just concatenates them into one. And it is commonly used after operations that create multiple P collections, like splitting or filtering. So you might see exam scenarios that mention these operations and ask what to do afterward. One of the options is to use flatten to combine them into one single P collection. So that was a little bit more in the weeds. There may be questions about these on the exam, so it still is important to understand. But that completes our coverage of the core concepts and terminology in Dataflow.